So we know key concept of line balancing. You understand the problem that we need to find out how many workstations, how many workers to produce according to my demand, to supply that demand. We understand that they have the different elements to create the long mold or whatever sandwich, whatever you're looking at, and you have to build that diagram with the relationship between them, right? The immediate predecessors, right? So now let's take a look at problem. So we received the same problem, but we received the latest forecast, and they want to design the line for 2,400 spreaders per week. Okay, and they will operate 40 hours per week. So they want to know what is the cycle time. The cycle time will be the pace of the whole process, right? So what that will be the time to produce each one of them. And I need to figure that out because I need to balance the workstation, and they need to be faster than the cycle time, or at least the same as the cycle time, right? So the cycle time here will be the cycle time that you need to have in order to achieve that demand, to produce according to that demand. Then we have other questions. We're going to go one at a time. So cycle time is going to be, first I calculate the output rate. So it's going to be desired output per day divided by available time. So 2,400, that was the demand. In our case, was for a week, not for a day, divided by hours in a week. So that's 60 units per hour. And 60 units per hour, that's the same thing of saying 1 unit per minute, right? And if you do 1 divided by 60 or 1 divided by 1, you're going to get 1 again. So it's the same thing as saying 1 minute per unit, or 60 seconds per unit, right? So every 60 seconds, I need to produce one of them in my process line, right? So I need to balance the workstations now to be exactly 60 or a little bit faster than 60, so I can supply that demand. To now I'm going to go to calculate the number of workstations, and to calculate the number of workstations, I need to find out what you call the theoretical minimum. So the theoretical minimum is the minimum number of workstations that I can have to actually supply in the pace of the cycle time. Okay, so the way to do that is just sum the total time that it takes to do one. So if we go back here, if I have one person doing the job, it will take 244 seconds, right? But I can't have one produce at 244. I need to have one item produce every 60 seconds. So how many people do I need to produce one every 60 seconds if when I have one person it takes 244? So that's what this math is doing. It's taking the 244, which is the total time if I have one person, and dividing that by 60, because I need to produce every 60 seconds. And the answer here is going to be how many people you need to actually produce at 60 seconds. And in our case, it was the 244 divided by 60. That's 4.067, right? And here you see the answer. We rounded up to 5 stations. Well, why is that? It's because I can't have 0.067 persons, right? Or people. I don't know the right English for that. So you need to round it up because you cannot have less than you calculate. That again, that's the theoretical minimum. That's what it calls a theoretical minimum, because the actual minimum is 5 stations, right? The theoretical minimum is 4.067. So now I rounded to 5, rounded up, and I know that I have 5 workstations. I can calculate efficiency as well, just taking the sum of the work elements here, so that's the 244 again, divided by the number of workstations, which we just calculated, that's 5, times C, which is the cycle time, which we just calculated as well, which was 60 seconds. Oops, 60 seconds here. Okay? So 244 divided by, where am I? Right. 244 divided by 5 times 60. That's the math that we're going to do. And we get an efficiency of 81%, right? So if you have 5 people there doing this work, their average efficiency will be 81%, means that the capacity cushion will be 18.7%. Okay? Finally, I already know that I need 5 workstations, but who's going to do what? I had more than 5 steps in the process. I need to understand who's going to do what. So the way to do that is I just take that diagram and divide the labor in a way, in 5 workstations, in a way that no workstation has a higher time than the cycle time, right, which is 60 seconds. And you have many possible solutions for that. So in this case, they divided A here, it's one workstation, C is another one. The third workstation will be doing activity B and F. The fourth workstation is going to be doing D and G, and the fifth workstation will be doing E, H, and I. So you can do more than one work element, and that's the goal. Find out how many workstations I need to have. And the last slide of chapter 5, yay, uh, are just some rules that we can use to how to divide the work. So in class, we're going to do a problem with theory of constraints there, of the first kind of problems we did with capacity. We're going to do a problem also about line balancing, okay? But there's some different rules here that they can have. For example, I can look and try to get the longest work element first. So I take the highest time and then try to plug other stuff around that. I can take the shortest element and try to plug others around that and see what would work. Most or fewer followers. Just some rules, and I think the one homework assignment actually ask you to do according to one of those rules. So just be mindful. Then you have to look at those steps and find out the rule and kind of start following that rule. Okay, so we're here. We're done chapter 5. It is a long, but it's a very cool one. We're gonna do some very, very cool things on in our class. Okay.